Okay, so let's start by proving that we can decompose a representation into some of the reducibles. So the key thing is something we discussed in passing in the example of S3. Maybe I think I never really formally defined what a subrepresentation was, so maybe it's defined to zeros. So V has an action at G, be a vector space and so on, like we've been having. A subspace is a subrepresentation is if and only if U is G stable. That is to say, if you have a U in vector space U, subspace U and G, then U GU belongs to U as well. So it's the natural definition. It's a subspace that is stable, is preserved by the action of the group elements. In the language of G modules, simply U is a submodule of V. So it's a natural concept, and what we want to prove is that if we are in this situation, subrepresentation U of V, so it has a complement W, which is a subrepresentation. So in other words, we can find W such that V is the direct sum of these two subspaces. And well, U is a subrepresentation by assumption, and W is also. So there's two possible approaches that I can think of, standard things. Let me mention the first one in some more detail, because this uses something that we'll come back to. So what we'd like to say is we can define W to be the orthogonal complement of U with respect to a Hermitian pairing, but not just an arbitrary Hermitian pairing that will just produce a subspace, but we want a Hermitian pairing that is G stable itself. So we want to give to V a pairing. So this is a bilinear map from V to V, from V to V to C. That is a bilinear. And so lambda U V is lambda UV, and U the lambda. I'm going to have, I'll try to be consistent, and this we are over the complex numbers, so Hermitian means that it's so if I change the order of the product, I get the conjugate. So I want a Hermitian pairing, so a non-degenerate pairing. In such a way that I can define orthogonal complements, and the orthogonal complement has the property of being an actual complement. So the procedure will be then to produce such a Hermitian pairing, and then it will follow from standard properties of Hermitian pairings, having a non-degenerate pairing, that the orthogonal complement will be a complement, and because it is G-stable, then it will be a subrepresentation. So let's assume we have this pairing, and just to be clear, what we want, G-stable means that for every pair of vectors in the vector space V, acting on by G preserves this inner product. Yeah. So this is what I mean by G-stable. So assuming we have this inner product, non-degenerate. Well, just to be clear, by that I mean that if this is 0 for all V, then U is 0. So somebody orthogonal to every vector is only the 0 vector. Then we take W to be orthogonal, then we know V is U direct sum U orthogonal because of the non-degeneracy. And now I want to show that W is stable by G. So if W belongs to W, I want to show that GW also belongs to W. Check this. So to do that, we check that GW is orthogonal to every vector in U. Now this, so take U and U, and G, because this is for all G and G. So if we compute this, we want to compute this inner product, but by the fact that our inner product is G-stable, this is the same as putting the G on the other side. And G inverse of U belongs to U because U is a subrepresentation. And therefore this is 0 because W is assumed to be in the orthogonal. And this is true for every U, and this implies that GW is in the complement, orthogonal complement, that is W. Okay? So basically we converted the question to a question of producing this inner product. And this is a typical situation that we want to we will encounter. We want to produce certain things that are fixed by the action of a group. And so the standard technique to produce something that is fixed by a group, if you can sum, then you can take the sum over all translates of your object. If the sum is, for example, finite, as we have, because our group is finite, then that will produce something fixed by the group. In the case if your group is infinite, then you would have to consider issues of convergence, which is an additional thing to worry about. So to produce H, we start with some inner product, let's say 0 on B, and we can construct it such that it's non-degenerate. In fact, we can take it to be positive definite. Right? I mean, you can take a basis of V, for example. So if V has basis V1 up to Vn, you can define the product such that Vi Vj is equal to delta Ij. So you just take the standard inner product. So 0. So Eg. So this is a basis. Okay, so if you just take an arbitrary inner product, the group G will change it. So there's no real chance that elements of the group G will preserve this product. You just completely randomly produce an inner product. So what you can do is, what I was saying is define H. I'm using H over this double bracket indistinctively, so let me use the brackets. So I want to define what the actual inner product would be, and so I can define it to be the average of all the values of the inner product that we've had over the translates by the elements of the group G. And here's, this is what I was saying. If you have something that in a group where you can sum, then the average, the sum of all the translates, would be fixed by the group. And as long as that sum makes sense, you can do this. Because our sum is finite, there is no convergence issues. So clearly, this is fixed, because if you act by the group, you will just rearrange the sum. Yeah. If I replace U and V by, say, G1 of U and G1 of V, I just have the same sum, but now kind of shifted around. Yeah? So maybe, should I write this? Let me try. So define this. This is the sum of G, G1, U, G, G1, V, 0. And this, I can just rename G, G1 to be G, and those, the pair G times G1 will run over the whole group again. So this is the same as this sum, which is the same by definition as our product. So this is all very good. We produce a bilinear pairing that is fixed by the group. But there is one thing that we should worry about, which is what? I mean, it's always fine to take averages and produce things that are fixed by the group, except there is one caveat. For all we know, what we just produce is the zero pairing. If you add, in any space, if you add the translates of a vector, you will produce something fixed by the group, but it may just be the zero vector, in which case it won't be very useful. You already know zero is fixed. So how do we know that this pairing, that I claim that this pairing works, that this pairing actually is good, is in fact non-degenerate? No, not just not zero, but it's non-degenerate. How do we know that? So the claim is that this pairing is non-degenerate, and therefore, by our previous discussion, this will produce this complement. That's right. So we start with something that is positive definite, right? And now we produce another pairing by summing all its translates. How do we know? I claim that this result is actually non-degenerate. What kind of pairing is this? What can you say about this pairing? Each term in here is what? Yeah?
Non-negative?
Is positive definite or non-negative definite. I mean, to be clear, what I mean here by positive definite is that this is an inner product which in general takes complex values, but for vectors, the same vector, this is a real number, and this is non-negative at 0 equal to 0 only for u equal to 0. So it's like a complex inner product. So if you have a positive definite pairing, then it is non-degenerate. And so to show that this pairing that we have is non-degenerate, it would be enough to show that it's positive definite. But it clearly is positive definite because it's a sum of positive definite things. Yeah. So if this u was equal to 0, if this were equal to 0, by definition this is this sum. But each one of these terms is non-negative, and in fact is actually positive. If u is not 0, because gu is not 0 if u is not 0. So each one of these terms, if u is not 0, each one of these terms is actually positive. Yeah. So sum of positive is positive, so is this. So maybe I'll say this. Okay? So the sum of these positive definite inner products is actually positive definite, therefore it's non-degenerate, therefore our previous argument of using the orthogonal complement works, and we have produced a complement of a representation which is itself a representation. But I went into some detail in the proof because what we actually did was a little bit more. We also produced a actual positive definite inner product that is fixed by the group. So the upshot of this is something we'll come back to, is that if you have a finite dimensional representation of a finite group, then it has at least one positive definite inner product on the space that is fixed by the group. Okay. There may be more than one. but this is something that we'll come back to. So a second proof. This proof that we gave uses quite strongly the fact that we're working on the complex numbers. You can also do the following. So you can look at the projection of the vector space V to U. Just find, so this is just as vector spaces. And what you would like to do is take the kernel of this projection, as that would give you a complement. But for this W to be a representation, you will want this projection to be itself a map. So we want pi to be G-stable, so be a map of representations. And if you just take an arbitrary projection, it's not going to be G-stable. So what you can do is, again, we have some element, and we can talk about sums. So let's say we call this thing pi 0. So you define pi. Again, you can take an average, and I'll just tell you what you could do. So you could take this. So pi of V, you can define it to be this. And then take W to be the kernel of pi. So I'll just give you the outline of how a proof will go. So you have a projection whose kernel is a complement, but the complement is just a vector space complement, and so you can fix that by kind of improving your projection into a map that is now actually G-stable by averaging, and then you take the kernel of that new map to be your, so maybe this W0 is just a complement. So it's a similar idea, and this doesn't, so there's a little work to do to check that this actually does what we want. But this doesn't really use the complex numbers. Okay, so as a corollary of what we proved, every representation is a sum of irreducibles. It's a direct sum of irreducibles. Because irreducible, maybe also should formally define it. We say V is irreducible, or U is irreducible by definition, if and only if, let's see, V, any proper sub-representation, well, the R node so if you have a representation, of course 0 is always a sub-representation. It's a vector space, so 0 that the group takes to itself, that's kind of tautology. And V itself is a representation because that's what you started with. But there could be things in between, and if there aren't, then you call the representation V irreducible. And the claim here, the corollary, is that the irreducible representations, by means of direct sum, give you all of them. So suppose we have a sub-representation V. If it's irreducible, then if V is irreducible, then we're done. It's a sum of irreducibles itself. Otherwise, it has some proper sub-representation U. By the proposition or theorem that we just proved, U has a complement, W, which is also a sub-representation that gives you V. Now, I guess by induction in the dimension on the representations, W and U are both representations that are of smaller dimension than V, because U is neither 0 nor V. So by induction, on the dimension V, I guess we should check dimension 1. I don't write all the details. U and W are direct sums of irreducibles. And so the whole V itself is a sum of irreducibles. So it's maybe worth pointing out that this is not a complete obvious fact, and there are many situations where this is not quite the case. So this statement, so this fact may fail in general. So let me give you some examples. So suppose if you're trying to do, say if you're trying to do things over the integers, for example. So if you look at CG modules, so it would be Z modules with an action of the group G. It may not be possible to write a module as a sum submodules. So if you look at the group of order 2, when you look at permutations, so just that G is, let's say, let me put it this way, so it's generated by sigma, where sigma is of order 2, then where sigma takes xy to yx, acting on z squared, then you have some modules, for example 1, 1, the line, this module spanned by the vector 1, 1, this is fixed by the group, is a sub-representation, and also the line, the multiples of the vector 1 minus 1. Right? So if I did this with field coefficients, z was replaced by even just the rational numbers, then this will be equal to the whole representation, to the whole space. But this is in fact is something of rank 2, but it's not the full thing. So in order to see this, to have any pair xy be a combination of these two vectors, you need to invert 2. Yeah. You need to take a half. So if you don't have a half, you won't be able to write the whole V as a sum of these two subrepresentations. Right? I mean, what we're saying basically is just that you can write xy as a half of x. Let's see how I want to say this. Yeah, so. So I can write x as u plus v and y as u minus v. But then u would be 1/2 of x plus y. V would be 1/2 of x minus y. So the vector xy, we can write it as the vector u times 1, 1 plus v times 1 minus 1. But u and v typically will require a denominator too. Okay, so just to make the point that what we just proved is not something completely obvious that always holds. It could be also the case that this is a problem somehow, that the ring doesn't have the things you need. I mean, you can have also something a bit more dramatic if you look at an infinite group, say Z, you map it to the matrix 1, 1, 0, 1. Now, this is not our case. The group is infinite, but this has only the space spanned by the vector 1, 0 as a subrepresentation. So there are no two subrepresentations that could add up to the whole thing. So in general, this is the difference. So something like this. So this is Z acting on C squared. The representation is not irreducible. It has a subrepresentation that is not trivial, not that's proper, but still it's not a sum of irreducibles because there's no complement. So something like this is called, you cannot decompose it into a sum, so something like this is called indecomposable. So indecomposable is not the same as irreducible. This is not irreducible. So in general, when you look at more general situations, you have to deal with indecomposables as opposed to just irreducibles. In the situation we're in, for us, irreducible is the same as indecomposable. Yeah? Indecomposable meaning you cannot write it as a proper direct sum of smaller things. So this is a special situation which is much more amenable to study. Okay. The next thing I want to show to you is something that is exceedingly simple, but incredibly useful, and something that appears constantly in discussions. It's called the Schur's lemma. So suppose you have two irreducible representations of a G and a map from V to W that is G linear. So it is a map of representations. It preserves the action of G on both sides. So if we have such a phi, then the first point is that phi has to either be an isomorphism or is zero. And a second, more precise point, if V is equal to W, then phi is actually a scalar. So if the scalar is non-zero, this is an isomorphism. If the scalar is zero, it's a zero map. So it looks fairly innocuous, but as I said, it's extremely useful and ubiquitous. So to prove one, it's actually fairly simple, because the point to make is that the kernel and the image of phi are subrepresentations, precisely because we're assuming that because phi is G linear. So these are subrepresentations. So kernel is sitting inside V and image is sitting inside W. And because we're assuming that V and W are both irreducible, then either the kernel of V is zero, or the kernel of phi is the whole thing, because those are the only representations, sub-representations there are. And similarly, the image of phi is either 0 or all of W. If the kernel of phi is 0, then the map is injective. And and therefore the image has to be W, yeah, or in the case that the kernel of phi is all of V, then the map is a zero map, and the image is V0. Yeah. So this is just a simple consequence of assuming that our representations are irreducible. The second one is a bit more interesting. So I'm assuming now V is equal to W, so I can speak of eigenvalues. So let's take an eigenvalue lambda of phi, and there is such an eigenvalue because we're working over the complex numbers. Okay. So we leave the field to be algebraically closed for this. So the kernel of phi minus lambda identity, this is non-zero by definition of eigenvalue. There is some non-zero vector in here. And it's a subrepresentation because phi is G-stable, and multiplying by scalars is certainly G-stable because we commute with everything that is scalars. And therefore, this map, phi minus lambda identity, is a subrepresentation that is not the zero representation, so it has to be the whole thing. So the kernel of this has to be all of V, because V is irreducible. But this means that phi is equal to lambda times the identity. Because phi minus lambda the identity is a zero map. Yeah? So phi is just a scalar matrix. Okay, so the first corollary is that if G is abelian and V is irreducible, then the dimension of V is 1. So the only irreducible representations of an abelian group are the one-dimensional representations. So prove this. So take G in G. Rho is our representation going from G to G of V. Rho of G by the previous statement. Now let's be careful. So rho G is somebody in G of V. Because the group is abelian, so this gives a map from V to V. Which is G linear. Right? because by commutativity, if I have some other row of H of V, this is the same as row of H, row of G of V, because the group is abelian. So row of G, viewed as simply as a linear map from V to V, commutes with multiplication by group action, and that's what we call G linear. And the statement of the corollary is that if you have a G linear map on an irreducible representation, it has to be a scalar. So rho of G is equal to some lambda times the identity for every G, and which means that any subspace of V is a sub-representation, because scalars preserve any subspace, just by definition of subspace. Hence, the only way that this can happen, because we're assuming that this only required that we're dealing with an abelian group, but we now use the fact that it's irreducible, and so any subspace is a subrepresentation, so every subspace has to be either 0 or the whole thing, and the only way that this can happen is the dimension of V is 1, because that's the only possibility for a vector space such that every subspace is either itself or 0. Right? If you have something of higher dimension, any smaller dimensional subspace will immediately contradict being irreducible. So that means that our representations are, for G abelian, are one-dimensional. So that means that V is dimension 1, so we really have the row is a map from G to GL1, which is C star. And we're assuming these are representations, so this is just a homomorphism. So i.e. what we called before a character. And if you recall, we did this the first class. We showed that so rho belongs to hom of G to C star, and we showed that this was a group which was non-canonically isomorphic to G itself. In particular, there are as many representations as the size of G. Right? So in a certain sense, what we're trying to do for arbitrary groups is done for groups that are abelian. And if all groups were abelian, the course would be over. The thing is that that's not true. The world is more complicated. And what we'd like to understand would be a similar statement for an arbitrary finite group. Now the irreducible representations no longer are going to be just dimension 1. We saw the case of S3. But it will be the case that we can classify them. And as I said before, there are finally many irreducible representations for a finite group. Okay. So to go further, we have to, well, not really have to, but it is a good point to discuss another construction of linear algebra that we are going to be using, which is the tensor product. So let me check how many of you are familiar with this.
For V-tensor product is just product of two vectors.
What do you mean by product? I mean,
After product.
sorry?
An after product.
Okay. Yeah, so let me just very briefly tell you a summary, and if you haven't seen it or don't recall, maybe you can look in a book on linear algebra that discusses this. I mean, there's a way to define it by means of a universal property, which makes it a little hard to understand what it is. I'll give you a more concrete way to think of it that is not as conceptual, but still is a useful way. So for the moment, let's forget the existence of these groups and how they act. We just have vector spaces. And again, always I'll stay with finite dimension. And also over the complex numbers. So we'd like to define what V tensor W is. So this would be another vector space. So if the dimensions of V are M and N, then this will be of dimension M times N. And a concrete way to think of it, as I said, not very conceptual, is as follows. If you take V1 to Vm basis for V, and W1 to Wn a basis for W, this tensor product will have a basis which is formed with pairs. So V tensor W have basis. So one possible basis would be formed by formal products of this kind. Indexed by a basis vector of V and a basis vector of W. And so this formal product is bilinear. And the thing that I'm interested in is how we're going to define V tensor W to be a representation when V and W are representations. So now I add the fact that V and W are representations of G. So we can make sense of GV for V and V and GW for W and W. Then if we have the tensor of two vectors v and w, we define this to be G of v tensor G of w. So, just to be clear, this vector speed v tensor w has linear combinations of pairs of these such things are called sort of pure tensors. Not every vector in the space is a pure tensor. If you add two of these, you just get the sum of the two things. It doesn't combine into necessarily a pure tensor. So this is a way to easily define it on pure tensors, but the pure tensors, specifically these, for example, span the space, so that tells you how the action is on the whole space. So okay, let me put this on hold for a minute, because I like to actually describe, for example, if we fix a basis, how does the matrix of G look like in this basis if we know the matrix of G on the basis for V and the corresponding matrix for the basis of W. Okay, but before that, let me introduce what will turn out to be the most useful tool, which are the characters. So we have a representation of a group. So rho is a homomorphism, but we're going to associate to it a function which we might use V as a subindex, or maybe rho, or maybe just chi by itself, depending on the. Sometimes, if the representation is clearly stated and there's no risk of confusion, we just call it chi without any label. So this is you simply do the following. If you have an element of the group G, you define it to be the trace of rho of G acting on the vector space V. So if the representation is of dimension 1, then the trace is just the number itself. I mean, rho is then just a number, a non-zero number, and the trace of a 1-by-1 matrix is the number itself. So this, in that case, is not anything new, but if the representation is a higher dimension, then this trace is only like a tiny little bit of the matrix or of the representation. But the miraculous thing is that this information on the trace will be enough to completely characterize the representation. And that's, in a sense, the key result of this whole theory. So here, maybe I should emphasize that character has sometimes can be confusing because it carries kind of two different, somewhat different meanings. If we have a group and we have a homomorphism to C star, this is called a character. So it's an actual homomorphism, it's multiplicative. But something like this is also called a character, and this is a bigger set than that one, because as we were saying, if the dimension of the matrices are 1 by 1, if our representation is dimension 1, then we do have something which is multiplicative. But in general, these maps, if the dimension of V is bigger than 1, are not multiplicative, because the trace of the product of two matrices is typically not equal to the trace of A times the trace of B. Okay, so these functions, which tell you what the trace of the matrix is, are not necessarily multiplicative, and typically are not going to be multiplicative unless the dimension is 1, but nevertheless are going to carry, as I said, basically all the information there is about the representation, or more precisely, these functions will uniquely characterize the isomorphism class of the representation. So, first of all, let's be clear that this function is uniquely determined by the isomorphism class of rho. So first of all, by trace, in the familiar sense, you would have to take a basis, and then you take the sum of the diagonal entries of the matrix. And if you take a basis, if you take two different bases, the matrices will change, but the trace will remain the same. The trace remains the same after changes of basis. And if you have two representations that are isomorphic, they differ by precisely a change of basis on the vector space, and so the trace doesn't change. So this is uniquely determined by, so chi is uniquely determined by the isomorphism class of rho. So that's one point. And as I said, we will show that the converse is true. If two representations have the same character, then they are actually isomorphic. The other observation in the same vein is that chi, so chi is simply a function from G to C. Yeah, there is a priori no algebraic properties of it. But we can say the following: chi of the conjugate of H is the same as chi of H, because the trace of a conjugation is preserved. Yeah? So a way to say this is that chi is constant on conjugacy classes of G. Okay, such functions historically are called class functions. So the point I'm making is that the character associated to a representation is a class function. Okay. And the space of all class functions will play a role as we move on. Perhaps maybe worth pointing out a couple of other things. What kind of number is chi of G? Is a priori a complex number, but we can be a bit more precise. In fact, we know a bit more about it than just that.
Some of values or
So a priori, the trace is defined of a matrix as the sum of the diagonal entries, and that's just a complex number. But it's also the sum of the eigenvalues of the matrix, yeah? And the eigenvalues of the matrix rho G are, as we said before, very special numbers.
Yeah, is
The roots of unity. Okay, so that means that chi of G is a sum of roots of unities. Okay, and so a root of unity is an algebraic integer, and the sum of algebraic integers is an algebraic integer. So chi of G is in fact an algebraic integer. So it satisfies a monic equation with integer coefficients. This will play a little bit of a role in what we discussed, not a big super role, but it's worth remarking. So this thing a priori takes values in C, but in fact it's kind of a special values. Then there's another thing that we can say, that its size is something we can also say. Well, chi is a sum of, again, a priori entries of the matrix along the diagonal, but also sum of eigenvalues. The eigenvalues are roots of unity, and there's as many as the dimension of the space. Yeah. So what's the size of a sum of roots of unity of which you have, say, n of them? Each root of unity is of size 1. Yeah, it's on the unit circle. So you're summing n numbers of size 1. So the most you can get is the dimension of the space. Yeah. So these numbers are then fairly restricted. Let's continue with some properties of this. If we have that V is a direct sum, then what can we say about the character of the sum? It is the sum of the characters, because you can think that the representation V, the way the G acts, it decomposes as a sum of blocks. One for U, one for W, and then the trace is the sum of the blocks, the traces of the blocks. We also discussed the the dual representation. So what can we say about the character of the dual representation? So the dual representation on G, we define it to be the transpose inverse, right? So the transpose doesn't change the trace. And what happens when we take the inverse?
Investigators of matrix, so
It's 1 over.
anyway, it's I think same, because these values are the roots of unity, and
Well, first, the eigenvalues of the inverse of a matrix are the inverse of the eigenvalues of a matrix. Yeah. And these matrices are diagonalizable, so, well, it does. In general, the eigenvalues of the inverse will be the inverse of the eigenvalues. So the trace of the inverse is the sum of the inverses of the eigenvalues. So a priori is a little, for a general matrix, it's not easy to say what the trace of the inverse will look like. But here, our eigenvalues are in fact roots of unity, and one property of a root of unity is that its inverse is equal to its conjugate. is because any element in the unit circle looks like that. So the inverse, in fact, is the same as conjugate. And so instead of summing the inverses of the eigenvalues, I can sum the conjugates. And the conjugate of a sum is the sum of the conjugate. So this is the same as the conjugate. Okay. So this character mimics very closely what we do in representations. And I'll come back to this, but the reason I was discussing the tensor product is because I'd like to point out that the character of V tensor W is in fact the product of the characters. And I'll come back to this. Okay. Another point, these are all very simple observations, but are worth keeping them in mind because they're going to be used in one way or another later on. One other point to make is that what's the value of the character at the identity? Yeah.
One. No.
Why should it be 1?
Because
It's
no,
not a
the
homomorphism.
dimension.
It's the dimension of the space. Because it's the trace of row of 1, and row of 1 is the identity. Because row is a homomorphism. Right? Finally, if V arises from a permutation representation, as we discussed, so given a permutation representation, we can produce a linear one, then the trace has a simple way to can describe it in a simple way in terms of that representation. So here the situation is we have G is acting on a set X, and we associate to that a vector space and an action of G on that vector space. So what is the relation between the trace of the matrices and the action on the set? So think of the matrices, perhaps. What kind of matrices do we see if we look at the representation that comes from the way a group permutes elements of a set?
Permutation matrices.
We get permutation matrices, and now we're supposed to take the trace of a permutation matrix. So what would that be?
Now the elements are going to change.
The matrices have ones in zero in each column and each row, depending on how the elements were moved. So the elements of the diagonal exactly correspond to elements of the set that have not changed place. So the conclusion is that this is the number of x's in the set that are fixed by G. Okay? In particular, this means that chi of v is an integer. In fact, it's a non-negative integer. So this singles out the permutation representations because typically the character values are going to be all kinds of things, not just non-negative integers. So the whole theory of representation of finite groups will boil down to understanding the characters of a finite group, because these characters will, as I mentioned, uniquely determine the irreducibles, and any representation is a sum of irreducibles. Okay, so the information of a finite group is encoded then in something called a character table, which consists of giving the values of the characters of irreducible representations, giving the values. Now, the characters are class functions, so they only depend on conjugacy classes. So we don't have to give the values of the function on each element of the group. We just have to give it on one representative of each conjugacy class. So if we take, for example, S3 that we worked out by hand, the way that this is usually done is like this. I'm going to list, so my representations, or rather the characters of representations, are going to be rows, and the columns are going to be the conjugacy classes, and I pick representatives of those conjugacy classes. Maybe I'll do this. 1, 1, 2, and 1, 2, 3. In S3, you either are the identity, or a transposition, or a 3-cycle, up to conjugation. So we just have these 3 possible types. And what information that we'll need to do calculations would be how many elements these conjugacy classes have. So how many 2 cycles are there? 3. And how many 3 cycles? 2. Okay, so typically you'll see a character table like this, or maybe there's more extra information as well. And now I'm going to list as rows of this matrix, of this table, the characters of the representations, of the irreducible representations. So we already classified those by hand. We had the trivial, the sign, and the standard. And I want to write down the character. So the trivial representation consists of always the number 1, so the trace is always 1. The sign representation is plus or minus 1, depending on the sign of the permutation, so the values are like this. Now, what is the character of the standard representation? You can use either what we did before, that we describe, in fact, the matrices explicitly, or you can use number 7. So the standard representation, recall, plus the trivial one is sort of the defining representation, namely S3 acting on the set 1, 2, 3. So to compute the character of V, it would be enough to compute the character of the defining representation and subtracting the character of U. But the character of U is just a trivial one. So, and the character of the defining representation is a permutation representation, so by 7, all you have to do is count the number of fixed points. So how many fixed points does the identity have on this set of 3 elements? 3, minus 1, coming from the trivial one, this is 2. This fixes 1 element, minus 1 is 0. This fixes no element, minus 1 is minus 1. Okay. So this is how all character tables of groups are going to look like, because we will prove that there are as many irreducible representations as there are conjugacy classes. So it will be a square matrix. And with this data, you can completely characterize a representation. So this, the data encoded in this character table, to a large extent, is all you ever going to need to study representations of a given group. So our goal will be to prove the statement like this for all groups. And yeah, so there's a few more properties about characters that we'll discover. But we have to go step by step. So why don't we do the following? Maybe this would be a good thing to do to get a little bit of practice with these tensor products. Let's look at the character. Let's look at the representation of V tensor V. V being the standard representation. Okay. So first, let's do the following. Let's call this thing W. According to what I mentioned, the character of this is the square of the character of V, which means that given that what we know here, we can just work it out. The character following the same notation will be 4, 0, and 1. Yeah? Certainly this is not irreducible, it's not in one of our rows, but it will, this representation is a sum of irreducible representations. We proved that earlier. So these VI's are going to be among those 3 that we have there. And if I compute the trace of W, this is going to be the sum of the chi VI. Yeah? So why don't we we'll find out what these VI's are by decomposing this function as a sum of these other three. Now, the group has three conjugacy classes. So a function that is constant on conjugacy classes has the space of such functions is dimension 3, right? Because what you have to do is give some value to these three classes. So, and we have three vectors that are class functions, and we could check, but it will be in general the case that these three rows are linearly independent. In fact, they're a basis for the space of class functions. So this will come all later, but what I'm anticipating is that I can write 401 in terms of a linear combination of three rows in a unique way. And we should be able to just spot it. So can we do that? How can we write the values 401 as a linear combination of these three? It looks like that's the sum of the rows. So in fact, chi of w is chi of u plus chi of u prime plus chi of v. And so what happens is that, I said this before, we will show that the characters uniquely determine the representations up to isomorphism. And so if you write chi w as a sum of irreducible characters, that's only one way to do it, and it corresponds exactly to decomposing the representation into irreducibles. So this simple linear algebra calculation we did in our heads exactly corresponds to decomposing w, so I can be sure that this is what happens. Okay? So this is what the beauty of this whole theory is, that the issue of decomposing the representation into irreducibles precisely gets translated into a simple, fairly simple linear algebra calculation once you have that table over there. Okay, so this is one of the amazing and beautiful facts about the theory, that in a way you can get away from dealing with specific vector spaces and matrices and the way the group acts and so on into something just much, much simpler, which is these the vector space of class functions. All right, so we'll do that next week. Let me just say one last thing, is that these vectors are not only linearly independent, but we're going to put an inner product in the space of class functions, and these rows, these vectors, are going to be an orthonormal basis for that space. So in fact, decomposing a vector into an orthonormal basis is even easier. All you have to know how to do is take inner products. So we don't have to guess or do basically any linear algebra in order to make this decomposition. So this information here is, as I was saying, contains basically all we ever want to know. Certainly all we want to know, all we need to know if all we want to do is decompose a representation into some of the irreducibles. Okay, so let's continue on Monday. Yeah?
I will erase the blackboard. I will do.
Oh, okay, sorry. Thank you.
Do we follow a particular book?
Yeah, I would suggest you have a look at Fulton and Harris, which is a pretty big book, and it's a little humbling, but we're not going to go past, I think, chapter 2. So it's a little condensed, but it's a very nice book. And I have some notes that I said I could make available to you, so I'll try to do that this weekend. Okay? These are notes of that I'm following. I taught this course many times before, and last time I taught it as CISA. Some students wrote up the notes, and so I'll give you that. then I think they did a good job. Sorry?